Hello everyone, I am Yaghavendra Kumar, a PhD scholar in the Center of Rural Development and Technology. I am doing the PhD under the guidance of Professor Kavya Dashora ma'am. So in this video, I am going to discuss about the PXRD. I will give the brief overview on powder XRD. So let's start. The topics which I will cover in this video is the introduction about the X-ray diffraction, then working principle, then its application, how can we apply these, then advantages and disadvantages of using this XRD, and then the conclusion, what are the conclusion of this overall. So first one is the introduction to XRD. XRD is the technique often known as XRD is used to examine the atomic or molecular structure of materials. By using this technique, we can identify the molecular microstructure of any material. It is a non-destructive and performs based on crystalline materials. So it is non-destructive. What does it mean? Non-destructive means without causing any damage to the original part. That is called the non-destructive. Uh, then because the substance being studied is often finely pulverized to a uniform state. Pulverized, that means to ground in a very fine powder form. The process is frequently referred to as X-ray powder diffraction. Diffraction is the small bending of light as it travels around an object's edge, hits a wall, or enters an aperture. So, when the incident light goes on the object and it hits on the wall, and when it bends, that is called the diffraction. The extent to which it happens is determined on the wavelength size in relation to the size of the obstruction or aperture it runs into. What is the size of the aperture and wavelength size? Based on this, it determines. Next, evolution of PXRD. How PXRD evolved. So in early stages, XRD was confined to single crystal analysis, as detection methods had not advanced to a point where more complicated procedures was able to be performed. After many years of discovery and refining, however, technology has progressed to where crystalline properties, structure of solids can be gleaned directly from powder sample. Gleaned directly, that means we are collecting directly from the powder sample, thus offering information for samples that cannot be obtained as a single crystal. One area, so the basically mostly the PXRD used in the pharmaceutical industries where drugs are analyzed in the through the powder X-ray diffraction method. uh, PXRD In PXRD, X-ray diffraction in powder is a popular technique for characterizing material at the nanoscale. Nanoscale, that means the size which is it is 10 raised to minus 9 meter. In addition to several microscopic and spectroscopic techniques, powder XRD analysis of a sample gives crucial information such as phase identification, sample purity, how pure our sample is. Then what is the meaning of phase here? So I want a clear bit about this phase. So phase is a crystalline solid with a regular three-dimensional arrangement of the atom. That is called the phase. So we can identify phase, sample purity, crystallite size, and in some situations, shape. Diffraction occurs when a wave meets a set of regularly spaced scattering objects, and its a wavelength of the distance between the scattering objects are of the same order of magnitude. Okay, so one question will arise in your mind, like why we are using X-rays only. So I am giving the answer here. X-rays suitable for crystallography as its wavelength and crystal lattice parameter are both in the scale of angstrom. Angstrom is equals to 10 raised to minus 10 meter. So how does X-ray works? X-ray is a type of electromagnetic radiation with wavelength that can be measured in nanometers. That is, 1 nanometer is equals to 1 billionth of a meter. Interferences results from the scattering of monochromatic X-ray. Monochromatic, that means monochromatic is nothing but the light rays with a single wavelength is called the monochromatic. So monochromatic X-rays from a material with this scale of structure. As a result of the positive and negative interferences, according to Bragg's law, there is a pattern of lower and higher intensities. Okay, later we will see in the graph what is the lower and the higher intensities. I will discuss. In response to X-ray wavelengths, the pattern which mimics the spacing of planes in a crystal lattice produces three-dimensional savings of diffraction with crystallite materials. These methods, called constructive interferences, is employed to investigate crystal structure and atomic spacing. Okay, then it's working. Then all diffraction methods start with the emission of X-rays from a cathode tube or rotating target, which is then focused at a sample. Okay, by collecting the diffracted X-rays, you can analyze the sample's structure. This is possible because each mineral has its a unique set of d spacing. Okay, so planes are there. The planes, there is a unique distance between that planes, and by analyzing that distance, we can identify the sample structure. Okay, and d spacing are the distances between planes of atoms which cause diffraction peaks. There are standard reference pattern and of d spacing which acts as a comparison when using XRD to identify the structure of a sample substance. The way that X-ray reveal the atomic structure of crystals is based on the Bragg's law. So first of all, I am a little bit explaining this structure. This diagram. Like this is the X-ray source A that you can see from these images. So as the rays going on the sample, so the beam which first falls on the sample, that beam which comes from the X-ray source is called the incident beam, and then after diffraction, means after bending of this beam, it goes to the detector, okay, which measures. So the angle, you can see that theta is the angle which made for this incident beam, and 2 theta is made for the diffraction. So later I will discuss why 2 theta we are taking for calculation. Okay, so let us see about Bragg's law. What is Bragg's law? Diffraction will only occur if the way the X-rays and substance is interact to meet the conditions of Bragg's law. This requires, what are those conditions? So first condition is the angle of incidence is equal to the angle of scattering. Second, the path length difference is equals to an integer number of wavelengths. Okay, so you can see from this diagram that this is incident beam, how this is coming, what is wavelength. One wavelength, that means how the cycle is going, then it is a one wavelength. Then after diffraction, it is that is the scattered beam. Then another beam is coming and it is striking on the sample surface, again it is diffracted. So by drawing a line between these 2 points, and then you are adding this CB to BD, you will get the path difference. Okay, and the D spacing, you can see from this picture that this is the distance between the 2 planes, that is the D spacing. Then the equation of Bragg's law relates wavelength to angle of incidence and lattice spacing, where n is what? N is the numeric constant known as the order of the diffracted beam. Lambda is the wavelength of the beam, d denotes the distance between lattice planes, and theta represents the angle of diffracted wave. The conditions given by this equation must be fulfilled if diffraction is to occur. Okay, so n lambda is equals to 2d sine theta. Okay, so note one thing here, like in previous slide, I said that I will tell you about the 2 theta, why we are taking 2 theta. Apart from these, one more important thing is that the crystal structure determines what crystal planes cause diffraction, and the angle at which they occur. The angles are shown in 2 theta, as that is the angle measured between the two arms of the diffractometer. So if you that incident beam which is making angle theta from this plane, so if you extend this forward, and then you measure the angle, then this is one theta, and another that diffracted beam made with the plane, from where from that plane that incident being made. So this if you add these two thetas, then you will get the angle 2 theta. Okay, so later on we will discuss for the paper ACS nano paper. So we will discuss here about the cadmium sulfide as an example. So this is a ubiquitous quantum dot material that is widely used in many nanoscience and nanotechnology fields. The quantum dot is nothing but is the tiny particle which falls in the size range between 2 to 10 nanometer. So when the crystalline size decreases from bulk to nanoscale dimensions, the XRD peaks Broyden. Okay, that is important. And how you will confirm this thing? You can see from the Sarad equation, which is the d is equals to k lambda upon beta cos theta. So theta here is the particular diffraction angle, which is measured here in radians rather than degrees. Okay, d is the crystalline domain size, beta is the full width at half maximum, k is the Sarad constant in most cases, which is taken as 0.9, and lambda is the X-ray wavelength. So the first three peaks in the CDS cadmium sulfide XRD pattern correspond to the 100, 002, and 10 planes. This is nothing but the Miller indices of cadmium sulfide, and these are highlighted in the Woodside crystal structure, which is showing the hexagonal structure in the inset to this figure. So simulated an indexed powder X-ray diffraction pattern for bulk 1 micrometer size Woodside cadmium sulfide. The inset shows the crystal structure of Woodside cadmium sulfide with the 100, 002, and 101 planes highlighted. So from this figure you can see that there are three planes. That pink one is the 002 plane. 002, that means it is going that plane is parallel to the x and y direction, but that is perpendicular to the z direction, that is indicated by this 002. And then 100 planes, and another one is the green one, that is 101 planes. So their peaks are also showing in the diffractogram as this intensity you can see from this graph. Later on, that a simulated powder X-ray diffraction pattern for Woodside cadmium sulfide spherical particles of different sizes that ranges from 1 micrometer to 1 nanometer. So means in this figure, from bulk 1 micrometer to 50 nanometer, slight peak broadening is observed. You can see from this figure. It is difficult to calculate crystalline domain sizes using the Sarad equation for particles in this size range, as most of the peak broadening is due to the instrumental effects rather than particle size effects. careful analysis must be needed here. Okay, so decreasing crystalline domain sizes from 50 to 25 nanometer causes more noticeable peak broadening. You can see from this figure, like intensity is nothing but the height of the peak, and broadening is the width of the peak, or width of that peak. Okay, so here you can see as the particle size are decreasing from 1 micrometer to 50 nanometer, 25 nanometer, 50 nanometer, 10, like that, and so on up to 1 nanometer. So initially in 1 micrometer the peak sharpness was high, but as the particle sizes were decreasing, the peak sharpness is lowering and the peak is getting broadening. Okay, so it is very difficult to analyze this small particle. Then another important aspects of this PXR is that its orientation is very important. Let's say for example that is spherical particles, drying them to form a powder randomly orients them, and there is a statistically random distribution of crystal plane orientation with respect to the diffraction angle. Okay, so you can see that is the randomly distributed, but in case of cubic and this rod shape, it is non-random distribution. And corresponding peaks, you can see how the peaks are differentiated. Okay, so it confirms from these peaks that if the shape is changed, shape or size is changed from of the particle, then it will show the different peaks in the PXRD. Okay, later on that testing of the different relative intensities, how we are getting. So to test the if different relative intensities are due to preferred orientation effects, the same sample can sometimes be prepared for XRD analysis in ways that either minimize or maximize preferred orientation. For example, that you can see the figure here. Okay, that is germanium sulfide. The corresponding XRD pattern in this figure, in this graph showing here. So experimental data for the germanium sulfide nanoseeds drop cast onto the XRD sample holder. So what is drop cast? Drop casting is widely used to prepare the surface of the chemically modified electrode, in which the modifying layer is composed of particles such as nanotubes or nanoparticle, and used for electrocatalysis, notably for chemical sensing as well as material evaluation. That is the dope casting. Okay, here simulated XRD patterns for bulk germanium sulfide with no preferred orientation and fully oriented germanium sulfide are also shown here. The experimental XRD patterns are distinct, and comparison with the simulated XRD patterns indicated that the drop cast sample shows almost full preferred orientation, whereas the powdered sample shows partial preferred orientation. Here I want to clear about the what is the preferred orientation. So the XRD powder method is based on the principle of exposing the beam to all possible crystallographic orientations. This is known as random orientation. A preferred orientation is defined as a bias of orientation of one or more specific crystallographic planes. Later on, let's see about the nanomaterial samples containing different subpopulation of distinct shapes and sizes. So how its peak are getting, we will get. So nanomaterial samples, let's say for example, here simulated powder XRD pattern for a sample containing 75% 5 nanometer wordite CDS particles, and 25% 25% 25 nanometer woodside cadmium sulfide particles. Okay, these are the two different sizes, 5 nanometer and 25 nanometer. The bimodal particle size distribution produces peak shapes that contain narrower tips. Okay, from the contribution. So as I discussed earlier, that if the particle size is bigger, then it will show high intensity, and less broadening. But in case as the particle size reduces, like in case of 5 nanometer, you can see from this graph that its peaks are broadened and intensity decrease. So if you mix these two particles, that 5 nanometer and 25 nanometer of Wurtzite CDS powder, then the resulting peak, you can see that the tip, which is sharp tip, you are getting from of this mixture, is because of this 25 nanometer. But the broadening in the bottom, in the tail part of these peaks, is because of the is because of the contribution of 5 nanometer particles. Okay. Another here, zinc blends cadmium sulfide mixture. So simulated XRD pattern for Wurtzite cadmium sulfide and zinc blends cadmium sulfide along with 1:1 mixture of the Wurtzite and zinc blend phases, both as 20 nanometer spherical particles. So here the particle size is similar. Okay, 20 nanometer. So and that is spherical particles. The zinc blend peaks overlap with some of Wurtzite peaks because it has a particle size which is same size, 20 nanometer. So what will happen? In this case, the zinc blend peak overlaps with some of the Wurtzite peaks, so the XRD pattern of the mixture appears to have higher relative intensities relative to Wurtzite for the peaks to which the zinc blend phase contributes. Okay, so you can see from this figure that if we mix both the things in 1:1 ratio, the peak intensity increased. Okay, then let us discuss about the applications of PXRD. So here phase identification is the first application. So I told you already about the phase. What is phase? Then so how phase identification can performed by PXRD, which is often accomplished by comparing an experimental XRD pattern with the reference pattern that is either simulated or obtained from the database. In such cases, an unambiguous and complete match, unambiguous, that means clear, okay, and complete match between the experimental and reference patterns is needed. To accomplish this comparison, experimental XRD patterns having sufficient signal to noise ratios are needed so that low intensity peaks can be observed. What is signal to noise ratio? You should know that it is very clear from this picture I have uploaded here, that signal, that is the sharp peak you can see, and noise, that is the bottom part, that is the noise. Okay. So phase identification by XRD for some systems, especially nanoscale materials, can be particularly challenging because of nearly indistinguishable diffraction patterns. For example, here is the gold and silver are both phase standard cubic metals that have sufficiently similar lattice constant, that say gold and silver nanoparticles. Okay, so in this case, it is very difficult to distinguish between these two metals. You can see from this figure also that graph showing the peaks which is almost similar for gold and silver because of this phase standard cubic metal. Okay, so if you mix both the things, then also you will get the same peaks. Okay, nothing. So it is very difficult to differentiate between these two metals. In these and other cases, additional characterization techniques are important for achieving phase identification. Then differences between the amorphous and nanocrystalline products. Amorphous is nothing but the arrangement of particles or lattice in a appropriate manner, in a well manner. Okay, PXRD can be used to determine the differences among amorphous and nanocrystalline material. However, one important limitation involves amorphous components that lack long-range crystallographic order. That is nothing but the it has a very less periodicity, that is repeating of the lattice. Okay, as they do not produce diffraction patterns with discernible peaks. An XRD pattern for a sample that contains a significant impurity of an amorphous component in addition to one or more nanoscopic crystalline components may look may look indistinguishable from a similar sample containing only the nanocrystalline components. Okay, so it is worth noting that XRD patterns for amorphous species can appear similar to those observed for nanoparticles having diameter that are less than 2 nanometer. Both would exhibit similar significant peak broadening. Then sample purity. Samples that produce XRD patterns having low noise to signal to noise ratios, including poorly crystalline material. Okay, nanoscale materials having significantly broadened peaks can contain large amounts of components that do not produce XRD peaks that rise significantly above the background noise. Low intensity peaks which may correspond to impurities. Okay, if intensity is low, that means we can consider that it has a more impurity. Can also be difficult to observe. The presence of asymmetric peaks may be due to the stacking faults and other defects, or distribution of compositions in compounds that could be present as alloys or solid solutions. So in this way we can analyze the sample purity. Later on, lattice constant. So first of all, you should know about the lattice constant. Lattice constant is nothing but the distance between the two unit cells in the crystal lattice. For highly crystalline bulk materials with high signal to noise ratios and sharp peaks, lattice constant are often reported to 3 or 4 decimal places with uncertainty corresponding to the last decimal place. To obtain such precise values, profile fitting and refinement are required. For nanocrystalline materials which have lower signal to noise ratios and broad peaks, such precision is in lattice constant is difficult to achieve. Sorry. Bigard's law. What is Bigard's law? Bigard's law is nothing but the empirical observation that there is often a linear relationship between the lattice constants. Okay, lattice constant and its composition. For example, Bigard's law would predict that the lattice constant for gold AU 0.5 Cu 0.5 alloy would be the average of the lattice constant of AU and Cu. Because of these relationship, XRD is often used to determine composition, and composition is used to predict the lattice constant. It is useful as a rough estimate but has some limitations. Therefore, whenever we are using this Bigard's law, we have to use this in addition with another characterization techniques. So what is the so we have discussed about the XRD, PXRD, and their working and different graphs applications. Now we'll see the advantages of PXRD. You can use PXRD to determine the orientation of individual grains of a crystal and to identify crystal structures in unknown substances. This technique will measure the internal stress, the size and shape of small crystalline areas, and measure the average spacing between the layers of rows of atoms in samples. It can determine their mineralogy. XRD will produce clear, unambiguous results. Unambiguous already I discussed, that is a very clear, very and as a technique is it is both powerful and rapid. Preparation only involves minimum sample quantities. These you grind into a fine powder with an optimum size that is less than 10 micrometer. Okay, interpreting the results of XRD is relatively straightforward. The X-ray diffractometer continuously records the data during the process and represents peak position and X-ray counts in a table. Okay, in the table, the Bragg's equation calculates the d-spacing of each peak. Once you will get the d-spacing of sample, you can compare this reading to the d-spacing of the known materials to identify the sample. X-ray diffractometers are widely available testing instruments, both as benchtop and portable models. There are some limitations also on the, you can say, disadvantage of PXRD, which are it's which are using it to identify a substance that is not known to you, then the sample must be single phase and homogeneous. The sample must also be very small in quantities of tenth of gram. Proper preparation of sample is crucial. If the sample is non-isometric crystalline structure, then indexing its pattern can be complex, where there are high angle reflections, peak or overlay can occur, and worsen. So what are the conclusion here? So here are the conclusion of powder XRD. That powder XRD provides useful information about the structure, phase composition, shape, size, crystallinity, and other important features of nanoscale materials. Although unambiguous sample characterization almost always requires complementary and experimental and or computational methods. XRD patterns for samples of nanoscale nanoparticles having different sizes and shapes can look different, and careful analysis of the XRD data can provide useful information and also help correlate microscopic observations with the bulk sample. It is important to recognize these capabilities and limitations of powder XRD for nanoscale materials when collecting and analyzing data, as well as to ensure that claims based on XRD data are accurate, appropriate, and not overreaching. So these are all the points which I have covered. Uh, Thank you.